Thank you very much, Shaheen, for the kind introduction. And thanks for coming during the exam session to the talk, and everybody on Zoom. I think we can get started. It's great to be here. And we're not flooded yet here, so that's good. Hopefully it'll stay that way. Okay, I'm going to talk about some of the work that has been happening in the RowHammer, RowPress space and DRAM. And feel free to stop me and ask questions. I don't mind taking questions. How much time do we have?
1 hour.
1 hour, okay. I have much more material than 1 hour, so we can usually talk a lot about this. Okay, let's get started. So when I talk about RowHammer to freshmen, and I actually like mixing some research topics when I teach digital design and computer architecture, I show this picture of a bridge because it's a great analogy, I think. This bridge is critical infrastructure, and it existed for a while, and then a bit flip happened to it. And this is kind of a RowHammer bit flip, right? Critical infrastructure is broken. This is a safety, security, reliability problem, robustness problem. And that bit flip can affect a lot of things, essentially. Somebody can attack their infrastructure this way, or the safety of a person on this infrastructure can be threatened because of this bit flip, right? I also use this picture. This could be familiar to folks. Folks are constructing Manhattan at some point in time, and they're sitting on this infrastructure, a rod. They're happy right now, but if a bit flip happens, they will not be happy in a second, right? So I think of actually robustness or security about preventing, it's all about preventing unforeseen consequences. And I think we need to think about things this way going into the future, because we are, as computer engineers, computer scientists, electrical engineers, building the infrastructures that will be used everywhere in the future, including the space. And if we actually don't design these such that they're not ready for reliable and robust operation, then we will have trouble. If you don't like that, maybe you like Mr. Bean. Mr. Bean is driving his self-driving car as his envisioning in the 1990s. And if he gets a bit flip over here, he won't be very happy. We're not there with self-driving cars, but I think these bit flips are going to be a lot more important in this sort of critical infrastructure. And this critical infrastructure is going to be everywhere in the future. Okay, so what is RowHammer and why am I telling you this? Essentially, RowHammer is the fact that you can predictably induce bit flips in today all commodity DRAM chips. At the time we first looked at the problem, it was about 80% of the chips that we tested. I'm going to tell you the story of it also. And it's also the first example of how a simple hardware failure mechanism can lead to a widespread system security vulnerability, as far as we know so far. If you know something else, please let me know and I'll correct this claim over here. And it's exciting because people who normally don't talk about hardware have started writing articles that look like this. Forget software. No, hackers are exploiting physics. And I like this because I like this, this lower level things that make things work in the end. Okay, we're going to get back to this. So let me tell you the story of how we stumbled on the problem and what we've done and what has happened in industry, what has happened in other areas, and hopefully we'll have a good discussion. Feel free to ask questions, as I said. So we've been working on memory for a long time. This is an area that I am quite excited about. And we were looking at how to scale memory into the future. And scaling is an issue because clearly we have data-intensive applications. We want large capacity memories, and we want reliability also on top of that. And we always argue that these issues are going to become much more difficult at the device levels and circuit levels. So we really need to have a more system-level perspective and design the memory system and the computing system together to fix these issues. I'm going to give you examples of what I mean by designing better controllers to tolerate reliability problems like RowHammer soon. But let me tell you about the scaling problem that we're looking at in main memory first. So main memory today is composed of dynamic random access memory, DRAM, and DRAM stores charge in this capacitor. And you need to have access circuitry to access that charge. And for this to work, both the capacitor, the storage device, and the access circuitry, access device should work reliably. Now, unfortunately, if you want to store more data, you need to pack more bits in a given millimeter square. You want to reduce the size of both of these structures, or everything essentially over here. And once you reduce the size of these structures, it becomes less reliable. There's a lot more noise, there's a lot more interference effects, and we're going to talk about some of those in this. So as a result, this is the scaling problem actually. And if you actually want to look at a DRAM chip, it doesn't look very nicely like this. It actually looks something like this. I'm not going to go into the lower levels of this, but people actually do a lot of really hard work to make these devices function. And functioning them reliability is a difficult problem going into the future. These capacitors are actually very deep inside the substrate. Okay, so we've been doing a lot of studies, as I mentioned, on DRAM, and this is one of the studies that we did with Facebook in 2013, 14 or so. It was published at DSN 2015. And essentially, in this study, we studied all of the memory errors that happen in Facebook's data centers all over the world. And this was a lot of memory, a lot of servers. They didn't let us publish how much because they were worried that it would affect their stock price because it would give out their infrastructure size. But this is a nice correlational study. In production data centers, we have a very strong correlation between the DRAM chip density that's employed in the server and the failure rate that we observe in real systems out there. So you can see there's a nice correlation, meaning that denser DRAM chips lead to more server failures because they are less reliable. This is because cells are smaller and cells are closer to each other. Okay, if you're interested, you can read papers on that topic. And we also wanted to actually understand these problems at a lower level in a more controllable way. So we actually designed these FPGA-based infrastructures where we could test the DRAM chips in as many ways we want. Essentially, we could change the refresh rate, we could change the latencies, etc. We could change the temperature with this fan and the earlier versions of it. Essentially, we built this infrastructure, and this is where we did a lot of the testing for the RowHammer studies. We open sourced it later on as SoftMC, and the more recent version is actually open sourced as DM Vendor, and I think it's being used by some folks over here who are familiar, and we're happy to support it if people are interested in supporting, and we've been working with folks here to support it. You can actually get your own FPGA, download our source code, and test any DRAM chip, and uncover a lot of interesting things. I will not tell you everything we uncovered in this talk, because there are a lot of exciting things that you can uncover in what happens inside memory. For example, you can do analog computation in real DRAM chips today by violating the timing parameters. This is something that people did not really think of in the past, but you could do it in real DRAM chips, even though they're not designed for that purpose. Okay, that's just a teaser for people who want to look at analog computing, for example. But I'm not going to talk about that. I'm going to talk about why we built this infrastructure. So we built this infrastructure to really understand what's going on in terms of the reliability and scaling issues in DRAM. And one of the major things in DRAM is data retention. DRAM is dynamic random access memory, meaning it cannot retain data over time. It basically loses charge over time. And you need to refresh every single cell in your memory. Right now, my cell phone is in my pocket, but it's wasting energy because it's doing self-refresh, essentially. And we wanted to get rid of this problem. And that's the reason why we built this infrastructure. We wanted to understand the retention characteristics of every cell in DRAM and figure out how we can get rid of this refresh in DRAM. I'm not going to tell you exactly how to do this. It's not an easy problem. But if you test DRAM, you will figure out that most of the cells can retain data for much longer than the rate at which we're refreshing DRAM today. So for every 64 milliseconds, every cell is refreshed. But you can actually, if you understand this retention time profile of cells, and if you're careful, you can get rid of most of the refreshes. And that was our goal. It's not that easy. That's why we built this infrastructure. And I'm going to, again, leave this as a teaser. We've been writing papers about this topic, how to actually get rid of refresh as much as possible, and studying it. I'm not going to bore you with more papers, but there are a lot more papers on this topic, essentially. I actually think this is an interesting problem, and we're going to circle back to this. Studying refreshes is going to help us in solving RowHammer more efficiently also. Okay, so while we were doing these studies, we actually looked at a lot of different failure mechanisms, and we were also doing studies on flash memory, which I will mention briefly later on. And we saw a lot of disturbance errors in flash memory. And together with Intel, we decided to study DRAM chips in terms of read disturbance. And we found that essentially DRAM chips are vulnerable. So what is this read disturbance phenomenon in DRAM, RowHammer phenomenon? If you look at DRAM memory, it consists of rows of cells. This could be considered a subarray. If you want to read cells in one row, data in one row, you need to activate that row, meaning you apply high voltage to the word line or open that row. And if you want to read something else, you deactivate that row, apply low voltage to that word line, or close the row. This is called precharge in DRAM. Now, if you keep doing this repeatedly, activate precharge, activate precharge, activate precharge, or high voltage, low voltage, high voltage, low voltage, etc., you will get bit flips in physically adjacent rows, some invulnerable cells. Now, clearly, this should not happen, right? You're just reading from this row, and you're not touching anything else. Nothing should change in memory. But we found out that some things are changing in memory, and we call them the victim rows, and we call this the aggressor or hammered row. And we found out that in more than 80% of the DRAM modules we tested, we get these bit flips. Don't worry about these numbers. All of these are relative, and these are not the best numbers. These are numbers from 2014 paper that we wrote, essentially. But many people have replicated these studies, including folks here. So the numbers change over time, clearly. But the fact that this exists, and the first appearance happened in chips that were manufactured in 2010, and everything we tested that was manufactured in 2012 and 2013 had these vulnerability essentially. Older chips were not vulnerable because we hypothesized that you couldn't do enough activations to induce a bit flip within a refresh interval. So the cells would get refreshed before you could actually induce these bit flips. So I'm going to talk about some of the reasonings for this. So why is this happening? I kind of implicitly said this. DRAM cells are too close to each other. They're not electrically isolated from each other. And when you're accessing one cell, you're affecting the values in nearby cells because there's electrical interference between the cells and the wires used for accessing the cells. This is called cell-to-cell coupling interference. And I like thinking of it as an abstract level. When you activate or apply high voltage to a row, an adjacent row gets slightly activated as well. And vulnerable cells in that slightly activated row lose a little bit of charge. And if you do this hammering pattern, activate per charge many times, charge in such vulnerable cells gets drained unless they're refreshed before that happens. So one way of solving this problem is clearly refreshing memory much more frequent. I'm going to talk about that, but that's a very bad idea. Why? Because we were trying to get rid of these refreshes, right? To fix the energy and performance overhead of those refreshes. So clearly there's a tension between these two scaling issues in DRAM, RowHammer and refresh. You can trade off one or the other, but I don't think we would like that trade-off. Okay, so these bit flips have actually higher level implications because you get a bit flip at the device level, and this affects your language and the runtime system and the algorithm because that bit flip is directly visible to everything that happens over here. This is in main memory. Everything operates on main memory. It's directly visible to your data structures, essentially. As a result, someone can take over your system or someone can corrupt your neural network. So many things may happen, essentially. When we first studied the problem, along with our paper, we released a source code, which is essentially user-level code, x86 code, only 6 instructions. You could modify it to be 5 instructions. What this code does is it bypasses the caches on chip, and it bypasses the row buffers in DRAM, which are essentially caches on the DRAM side. And it essentially selects addresses X and Y, such that hopefully they're in the same subarray over here. And basically ping-pongs activations to X and Y, like this. And with this user-level program, we were able to induce bit flips. We also observed that you could actually induce even more bit flips if you were a little bit smarter about how you selected X and Y. If X and Y were such that there was only one row between them, you would actually get a lot more bit flips in that row that was sandwiched in between. This is called double-sided RowHammer, and later works actually exploited this to induce even more bit flips than we actually showed. So this is fascinating, clearly. We showed with that program you could induce errors in real systems. There's nothing special about Intel and AMD. Those were the systems that we had in our hand at the time. But any system with a good enough memory controller, which is not very hard to design for this purpose, can actually have bit flips. And clearly, this reliability, security, and safety issue. And we argued that this is actually a security issue. I'm going to read the first sentence of the paper that we wrote at the time. Memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I strongly believe this still. We should really keep this invariant. And in the paper, we said that someone can take advantage of these bit flips. They could hijack your computer, or they could corrupt your data, or they could basically cause system failure and system availability issues. And while we were actually looking into this in more detail, these good folks, these security experts from Google, Project Zero, they basically showed essentially what we were thinking about, which is great, I think. If someone takes your idea and shows that it works in the real field, especially Google, that's great. In this case, this is a direct copy and paste from their blog post. They wrote a blog post about it. They basically tested a selection of, they learned about the problem from our paper. They wanted to replicate it, and they were able to replicate it. And they built 2 working privilege escalation exploits. One of them takes over the Google native client, which essentially escapes the sandbox of a virtual machine. The other one is even more interesting. It does an attack that's called page table spraying at a user level process. That user level process can induce bit flips such that it can become root on the system. It can take over Linux, and it can do anything to the system, essentially. I'm not going to go into the details of the security. There's actually a huge literature on security on these sort of RowHammer attacks and bit flip attacks. But I'll give you the basic idea. The basic idea is they were able to, this user level program was able to hammer its own page table entries, and it was able to induce bit flips in its own page table entries that point to its own page table, meaning that it could gain write access to its own page table. And once a user level program is able to modify its own page table, all bets are off. Then you can actually take over the entire system. You can write or read from any part of memory that you're not supposed to read. And you can actually become root that way. It's a beautiful attack. And these folks actually have a beautiful black hat presentation. If you're interested in security, this is a good place to start. Although there's been a lot more literature on top of this after that. Later, this became famous as the RowHammer vulnerability. And one famous hacker on the internet said RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. So if you're actually stuck in this room, don't worry. And if the doors are locked, keep banging on the walls. And if RowHammer is in effect, magically some door will open. It's interesting. It's all about electrical interference, right? Okay, so I will not go into a lot of detail, but there's a lot of security research. Later, these folks from TU Graz showed that they could exploit RowHammer to induce bit flips on a remote machine, and they could take over that remote machine. These folks from Vrije University Amsterdam showed that you could actually induce these on a cell phone and take over someone's cell phone. I don't know if you can still download their application on an Android phone, but you could try it. People show that you could execute these attacks with a GPU. People show that you could do these attacks on a remote direct memory access in a data center. And these folks showed the same thing. And you can see there are a lot of interesting hammers coming here. People show that even if you cannot take over someone's system, you could read private data that you are not supposed to read. So you can break confidentiality in addition to integrity. And more recently, people have been looking at bit flip attacks where they show that you could actually degrade the accuracy of deep neural networks significantly to the point that they're essentially useless. And I think Shahin's group is actually exploring a lot of these deep neural network attacks also. I don't have all of these attacks. There's many literature on this topic, but maybe this is one solution to these attacks, right? To attack your computer and get rid of it. I don't advocate this, of course, right? Clearly. So, okay, there's a lot more here, and we've written a lot of retrospective papers. This is actually a nice starter paper. It doesn't cover all the research since it was published in 2019, but it covers research from all the way from device level to high-level software level. So if you want to get started on RowHammer, I'd recommend this one. And we've written an updated version, but even this doesn't cover the research that's happening in 2023. So there's this an active area. I'm going to tell you a little bit about the story of what we did in 2014 and then talk about what happened afterwards. Because what happened afterwards, I think it's very interesting also in terms of like how industry behaved and also how academia behaved. Any questions so far?
Yes. Can you, by hammering in one row, that you mentioned that you can have other bit flips? Can you control the type of bit flips you can have in the next row?
So that's a very good question. You cannot necessarily control, but once you induce a bit flip in a particular bit, you know that you can induce that bit flip again and again and again. So it's very predictable. Yeah, you cannot arbitrarily decide which bits are going to flip because that's really a function of the underlying circuitry and device. But the bit flips are very predictable. So what you can do is you can actually somehow create a template of the system and basically figure out which bits are vulnerable over time and then launch the attack at some point. Thank you. Sure, you're welcome. Okay, go ahead.
For the same reason, if you can figure out when it's vulnerable for an attack, could you not also like make it from defense? Like it's going to be weak at this point. Flip it then or just
potentially, yes. I think a lot of the understanding that you develop to do an attack can be used for defense as well. So defenders and attackers actually should be competing with each other. I'm going to mention that in a lot of the studies that we've done. That's a very good point. Okay, yes, another question.
So RowHammer requires two specially placed memory rows for a program to have access to work, right? Is there any reason it can't be mitigated just by the kernel refusing to allocate a program such adjacent rows in its page table?
So I think people have proposed software level mitigations to do isolation, for example. I think that's what you're getting at. They tend to be very costly in terms of memory space.
I imagine just splitting up a page into a dozen different pointers would probably not be great for me.
Exactly. Yeah, but people are looking into that sort of mechanisms, certainly. There's a very nice protection space. I will mention part of it. Okay, very good. So let me give you some analyses that we did in our original paper, and then I'm going to talk about what has happened. So we did a lot of studies with this infrastructure. That's the beauty of building infrastructure, I think. And we studied more than 120 modules at the time. And essentially, we concluded a lot of things. I'm not going to bore you with everything. But one of the things I will mention is you need to be, oh, somehow this moved and online it didn't move. Okay, there's a delay over here. Yeah, basically, we wanted to study from the memory controller's perspective, what's the difference between the victim address and the aggressor row's address? And most of the time, these are adjacent, but there are some cases where victims and aggressors are not adjacent. Now, this doesn't mean that they're physically far away from each other. This just means that there's some internal mapping or remapping of the addresses that happens in DRAM that obfuscates things. And this happens for fault tolerance and reliability reasons. They map, for example, they do row level remapping if a row is faulty for some reason. So this, the reason this is interesting is if you're building a defense at the memory controller and the software level, and if that defense relies on your knowledge of physical adjacency of rows, you need to be very careful. You cannot just assume that the addresses that you see from the memory controller perspective are going to be physically adjacent at the DRAM level. Okay, so there's another thing that one solution is potentially reducing the access rate, access interval. If you actually reduce the access interval significantly, you can get rid of all of the bit flips, but you have to throttle the accesses a lot, meaning instead of being able to activate a row every 50 nanoseconds or so, you have to increase that to every 500 nanoseconds, and it's not good for performance. So you need to be very careful in terms of access throttling. And by the way, these are real data from real chips, the worst chips that we tested, but these are not necessarily the worst things today. This is data from 2013. We're 10 years ahead, and 10 years circuit technology scale. And as a result, we're much more vulnerable today, as I will show you. And then the next lever that we kind of mentioned, refresh interval. If you actually reduce the refresh interval, meaning increase the refresh rate, you can reduce the errors that you get for RowHammer because you give the attacker less time to be able to induce a bit flip before the cells get refreshed. But at the time we tested these chips, you need to increase the refresh rate by 7x if you wanted to get rid of every single bit flip. And this was not the worst pattern. And today it's much worse, basically, as I will show you. So this is a bad idea in general, increasing the refresh rate. Okay, data pattern is interesting because different data patterns cause different amounts of charge coupling between cells that are adjacent to each other. So some data patterns actually lead to a lot more errors because they cause a lot more coupling capacitance. And this can be exploited also. There are a lot more observations that I'm not going to go into in detail, but errors are repeatable. I mentioned this earlier. You get as many as 4 errors per cache line at the time. That number increased over time. This means that simple error correction mechanisms that are employed in DRAM chips don't work. And you need to have stronger error codes. And that's actually very wasteful also. And we talked about double-sided hammering. Okay, so I think that's very interesting to understand this phenomenon. And our infrastructure enabled us to understand. I'm going to talk about some of the other papers that we've done. It's getting much worse. It has many dimensions. We don't completely understand, essentially. Word line voltage is interesting also. I mentioned that. But any DRAM chip is vulnerable. HBM chips that are heavily used in machine learning infrastructure today, for example, in GPUs, they're actually at least as vulnerable, if not more vulnerable. And we've been doing some studies on this topic. I won't have much time to talk about everything clearly, but if people are interested, I'd be happy to talk about it. But before I go into what happened, I will mention some solutions first. And then we're going to talk about the history of it a little bit. So I think when we discover a problem like this is a problem in the field, right? All of the chips in the field are vulnerable. Well, all maybe. Most of the chips in the field are vulnerable. And so you need to protect those vulnerable DRAM chips, meaning that you need to have some immediate solutions. And immediate solutions are clearly limited by what you can do in hardware and software. Longer-term solutions can be much more intelligent and interesting, of course, and we're going to talk about some of those. In our original paper, we proposed both types of solutions. This is a more general view of the solution space. More robust DRAM chips using different devices, better isolation material. That's very interesting, but unfortunately, it's very costly today. Error correcting codes, I don't think this is a good solution, as I mentioned. Fundamentally, I think error correcting codes are not a good solution for another reason, not just because they're costly, but because error correcting codes are very good if you don't know the source of the error. They basically are good at protecting random errors. Here, we know the source of the error exactly, right? Somebody's hammering this row. Increasing the refresh rate, we discussed this. Physical isolation, as was mentioned. People have examined all of these solutions. Reactive refresh is interesting. Basically, you somehow figure out which rows are being hammered a lot, either using probabilistic or deterministic approaches, either counters or sampling, and you refresh the adjacent rows, physically adjacent or vulnerable rows. And then proactive throttling means you do the same thing. You probabilistically or deterministically figure out which rows are being hammered, and then you throttle accesses to those so that you don't hammer more. I think these two are actually the most promising solutions that are being investigated today, except the difficulty is there's a huge trade-off space between cost, power, performance, and complexity. I'm removing security here because security, safety, you should get rid of bit flips. That's what I'm assuming. But you could also add that to the trade-off space if you can tolerate some of the bit flips, which is interesting. Okay, so what happened in industry? Basically, clearly, not all of these are possible immediately. Industry immediately reacted to it, and I like using Apple's security patch over here because they actually reference our paper also, and also Google's work. Basically, they increase the refresh rates because this is the only thing you can do actually in a memory controller at the time. I'm going to argue for programmable memory controllers later in this talk. You should have much more intelligent memory controllers that can fix these issues with better patchability. Increasing the refresh rate is not great, but they did this. They didn't say by how much. It's probably about 2x. Okay, but it's not special to Apple. Essentially, all industry released similar patches for their memory controllers. So what was our solution at the time? The solution doesn't work very well today because RowHammer has become a much bigger problem. But our solution at the time was probabilistic. Basically, we designed a memory controller. After closing a row, it probabilistically activates its neighbors with a low probability. You can set the probability as a user, potentially, or dynamically it could be determined. And we showed that this actually works nicely. If you're paranoid, you can actually increase the strength of that probability to higher values. And this is nice because it's actually very low overhead. It's stateless. You don't need to keep track of any rows, essentially. And its power and performance numbers are pretty good at that time. So here, the solution works because at the time, you needed to do a lot of hammerings to induce a bit flip. So just to give you a number, our initial testing showed that you needed to hammer a row 139,000 times to induce a bit flip. You could do it within the refresh interval at the time. Today, that number has gone down by 2 orders of magnitude almost. Well, around 2 orders of magnitude, actually. Yes, that's true. Okay, so para was actually nice because it was actually implemented in DRAM chips and memory controllers in some way. And you could actually do that. I'm not going to go through this in detail. And actually, Intel designed this controller that implemented a para-like mechanism that is inspired in the BIOS. That's not exactly what we envisioned, but you could actually change the BIOS and pick your hardware RowHammer protection or 2x refresh. If you pick hardware RowHammer protection, you need to choose a probability. Basically, the probability could be this. Hopefully, you don't choose every other activation to refresh your rows, right? So this was a step in the right direction, right? People were actually designing memory controllers that could mitigate the issue, and we thought it would go nicely. And I think it actually kind of rhymes with, or it's in line with what we have discussed earlier, right? We always argued for having intelligent controllers in memory for security, safety, reliability, and scaling. This was an example. Here I will take an aside. So this is actually the FPGA-based infrastructure that we used to have for flash memory. We did a lot of flash memory testing. And if people are familiar with flash memory, this is a memory technology that's clearly has very interesting applications today, right? I don't think the cell phones would have been possible without flash memory, in my opinion. But this memory technology, if you look at it, if you manufacture the bits, and if you don't design a controller with it, most of the bits are not reliable. What really makes this technology work is cooperation between the controller and the device. Controller really understands the voltage levels of the different cells. It basically tunes the voltage level such that you minimize the bit flips that you get. And controllers have a lot of error correction, etc. And we have a lot of work in this area that I'm not going to talk about, but I think this is a fascinating area. I think a lot of the emerging memory technologies need to have this sort of controller going into the future as well. But this is one paper that we've written that summarized a lot of the research and industrial work that's going on in solid state drives. So this is the sort of controller that I'm envisioning basically for DRAM, but it's on DRAM, it needs to be a much lower, lightweight controller. Okay, so before I go into the story, I will mention that I think we still need to understand a lot more. There are many effects that still need to be rigorously examined. We don't quite understand everything in DRAM. Aging is something scary, for example. If you use memory chips that are 20 years old or even 5 years old, how does RowHammer change? And there are many others, regulatory factors, and solving is clearly important also. Okay, so what happened? Essentially, Intel designed this memory controller. After that point, memory manufacturers said we solved the problem. They didn't say how, but they just said they actually have papers and public statements saying that we, in DDR4, we fixed the problem. So our chips are RowHammer free. And everybody somehow believed them. This is the interesting thing in industry. So we, of course, questioned this. I'm going to tell you about how we questioned it. So we revisited RowHammer, both at the lower circuit level. We just wanted to test the devices without RowHammer protections. And also, we wanted to test the devices that have these RowHammer protections to see if we can bypass these RowHammer protections. I'm going to tell you the first study that made us essentially question this a lot. Meaning, is it really an easy problem to solve? And can someone claim that they solved the problem without actually proving that they solved the problem? So this is the paper that we wrote 6 years after our original paper. This was also published at ISCA. Essentially, we did a much larger scale study. We studied more than 1,500 DRAM chips. And these are the findings. We found out that newer DRAM chips are much more vulnerable. You get many more bit flips that are happening earlier. There are some chips whose weakest cells failed after only 4,800 hammers, meaning that solution to the problem is not easy. And chips in newer technology are actually much more vulnerable. And existing mitigation mechanisms that we know of are not effective at future technology nodes. So if this scaling problem continues into the future, we don't have a solution basically. That's what this paper demonstrated. Let me give you, these are basically the types of DRAM that we tested. We built a lot of infrastructure for this paper basically. And this is one of the things that we measured. Essentially, this is the hammer count on the x-axis for different manufacturers, 3 different manufacturers. And as hammer, and these are different devices. On the y-axis, you have the RowHammer bit flip rate. So lower is better over there. And if you go from DDR4 old devices to DDR4 new devices, you get bit flips earlier, happening at smaller hammer counts, and you get higher bit error rates. Meaning that newer devices are a lot more vulnerable, essentially. And this is very common, as you can see, it's consistent across different manufacturers. Okay. So this is the mechanism, mitigation mechanism study that we did. This is hammer count on the x-axis again, going from high to low, from left to right. We're marching towards lower hammer counts to induce bit flips. These are real numbers from DDR3 and LPDDR4 devices. And y-axis, the normalized system performance impact of different mitigation mechanisms. So higher is better. Ideally, you're at 100%, meaning you don't have any performance impact. Increasing the refresh rate is terrible, as you can see. Basically, you get 80% degradation in performance. And then you don't need to study it, I think. That's not interesting. And Terra is the solution that we discussed in our original paper. You can see that it's also losing performance significantly if you get bit flips around 1,000, after 1,000 hammers, for example. And then even the ideal mechanism is not great, as you can see over here, but it's better than everything else. So basically, we said that we need to develop much better mechanisms to solve this problem at low performance overhead. And there's a lot of work that happened after that, some of which I will mention. But we need more work, basically, because one of the things is we don't know what's missing, essentially. That's why we study RowHammer characteristics. A lot of these works assume that you know exactly when a bit flip will happen. Right? But that whether or not a bit flip will happen is dependent on many conditions. It's dependent on temperature, it's dependent on aging, it's dependent on many things, and we need to understand these. That's why we had a deeper look at RowHammer sensitivities. I'm going to mention this relatively quickly. Basically, we studied temperature, aggressive electric time. I'm going to skip this because I have something else to talk about, and then physical location. And we see significant dependence on these parameters. So, for example, a RowHammer bit flip is more likely to occur in a bounded range of temperature in a way we don't quite understand. So you cannot basically say a RowHammer bit flip is going to occur at higher temperatures more. That's not the case, basically. It's really dependent on the cell and the temperature range, which means that we don't quite understand this relationship at this point, and we need to do more studies. I'm going to skip the second one. There's a huge spatial variation. That's actually interesting. Basically, certain physical regions of the DRAM chip are much more vulnerable to RowHammer. And if you can actually understand this, from an attacker perspective, you can attack those regions, right? And from a defender perspective, you can protect those regions better, right? And then spend less effort on protecting everything else. So you can actually use all of these in understanding from an attacker perspective as well as a defender's perspective. I'm going to skip that. I'm going to mention this basically. So this is actually a very common finding we found. If you look at all the DRAM rows, 10% of the DRAM rows are much more vulnerable compared to the other 90%. If you find a mechanism to actually protect them more easily, you have a better protection mechanism. We have a paper coming up at HPCA 2024 that actually studies the situation much more. But I think the solutions are not easy to develop. So this is an area of potential investigation. Okay. We did analyze the word line voltage. I'm not going to talk about this in detail, but you need to build more infrastructure. The reason we analyze the word line voltage is because RowHammer is directly dependent on the word line voltage, right? If you reduce the voltage to activate a row, you actually reduce the vulnerability. And we wanted to understand how much you can reduce this vulnerability, and can you actually get rid of the vulnerability this way? And the final answer is no, you cannot get rid of the vulnerability, basically. You can reduce the vulnerability, but you cause other issues like latency and data retention time. You could potentially navigate the space and find a reasonable solution, but this makes things a lot more complex. This is actually a place where I very much empathize with the DRAM manufacturers, because DRAM manufacturers are dealing with a lot of these things at the same time, right? Vulnerability, latency, retention time, and they need to get all of them reasonably right. Okay, that was a teaser, so I'm not going to talk about that. I'm not going to talk about HBM chips also, but I think this is fascinating. I think our machine learning infrastructure is very much dependent on HBM today, and they're as vulnerable, if not more vulnerable. And I think this is going to be an even bigger problem into the future. There's more studies that need to be done, but let's now go back to solutions. Are there questions? I feel like I'm talking a lot, but yes, please go ahead.
So on the topic of intelligent memory controller, I was just thinking of something. I know we have like active, reactive refresh as a potential solution, as a throttling. What about having a potential decoy row? It's more subject to being attacked, but it actually takes the attention away from the other rows that have victims around it.
I see.
Potential mitigation technique forward.
I mean, it needs to be investigated. I think it depends on how you design the decoy row, right? Maybe we can talk about it afterwards. There could be something there. Okay, so I'll move on. So basically what happened in industry, DRAM manufacturers said that this is, DRAM chips are not vulnerable. And we showed that actually in our 2020 paper that they're actually much more vulnerable. How did you solve the problem? But we also wanted to demonstrate that existing solutions are not really good enough. So this is the paper that showed that the solutions that are adopted by industry do not work. I'll give you the basic idea. Essentially, industry reacted to RowHammer using this TRR. TRR is target row refresh. It's a very nebulous thing in the DRAM standard that doesn't say what they do, basically. You can refresh target rows. It could be that way. So, from our hypotheses, we hypothesized that internally they would keep track of which rows are being hammered, either deterministically or probabilistically, and refresh the adjacent rows based on what we have proposed, actually. And we wanted to understand this. So we reverse engineered the underlying DRAM chips using our soft MC infrastructure at the time, or early version of DRAM vendor, let's say. And we introduced a many-sided RowHammer attack that would bypass the mitigations. And the idea is very simple. You hammer, instead of hammering 2 rows, you hammer many rows so that you overflow the internal tables that are tracking these aggressor rows. And we were able to do this basically essentially for all manufacturers. And to be able to do this, we did reverse engineering, and we actually provide an automatic tool people could use. They're actually much nicer tools right now, like Blacksmith and Smash, that Kaveh Azavi's group developed after that. So you can actually use them as opposed to Trespass today. So let me give you an example. These are some many-sided kamikaze. These 2 rows are aggressive rows, and then you have another row. So if the DRAM chip is able to carry only 2 rows, you would bypass that, right? And this is a 4-sided pattern here, for essentially 4 aggressor rows. And you can see these are data from real DRAM chips. In some cases, you get bit flips after 5 aggressor rows. In some cases, you get bit flips after 9 aggressor rows over here. And this is all of the chips that we tested. We were able to induce bit flips in all 3 major manufacturers, not in all DRAM chips, but we're going to fix that in the next work. And you can see that in some cases, the best hammering pattern was 19 cycles. So you hammer 19 rows and you get the best bit flips. And then we actually show that on real cell phones, mobile phones, you were able to induce bit flips, and you would actually induce these attacks that people have proposed in the past, including cryptographic attacks over here. So once you get a bit flip, basically you could induce any attack in the past. But it may take time to demonstrate that attack, of course, right? Okay. So essentially, Trespass showed that RowHammer is still an open problem, and security by obscurity is likely not a good solution. I still believe that, actually. I think we should be much more open in how we secure our systems, because as I said earlier, this is going to be our critical infrastructure. And if we trust someone to say, oh, this is secure, that's probably not going to work, because under what conditions is it secure becomes a quick question, right? Okay, so these 2 works that were published in 2020 actually triggered a lot of, let's say, churn in JEDEC. JEDEC is the major place where standards of DRAM, for example, are discussed. And they finally released these RowHammer mitigation papers, which are interesting, but I don't think they say much, let's say. But at least the industry is working on the problem. And especially hyperscalers like Microsoft, Google, they were actually pushing very hard on the DRAM manufacturers to solve this issue because they're the ones who would be most affected, right? They're the ones who are buying the most DRAM chips. Okay, since we don't have a whole lot of time, I'm going to quickly go over some of the other work. So basically, you can say, okay, you uncovered some of the bit flips, right? You didn't uncover the underlying working of these mitigations. And in the next work, we did that essentially. Using our infrastructure, you could actually figure out what's going on inside the DRAM chip almost exactly. It just is a matter of time, how much time you dedicate to it. In this particular work, we use data retention failures as a side count to detect when a row is refreshed by target row refresh. Essentially, what we do is we access DRAM with a particular access pattern, and normally we figure out the retention time of a row, and normally that row should lose data if you don't refresh that row for a while. But we found out that that row doesn't lose data because there is some internal refresh going on, and that internal refresh is happening because of target row refresh for RowHammer mitigation. So by understanding the retention failures in DRAM, you could actually figure out what's happening in DRAM a lot. That's why I think that investment that we made into understanding the retention failures was actually a good thing, even though refresh is a tough problem. Okay, so basically, you could reverse engineer essentially all DRAM chips over here. I'm not going to go through this in detail. There are a lot of interesting things, but essentially the underlying solutions at the time were not perfect or imperfect implementations of sampling-based mechanisms like para perhaps, and counter-based access mechanisms. Going forward, I think we need to do better, and we also show that ECC doesn't work unless you go to very high protection levels. Okay, industry was doing a lot of things. I don't have time to go through this, but I mentioned this paper because it's very interesting. Google, for example, released an attack paper in 2021. Microsoft also had a paper at ISCA that talks about coherence-induced hammering, for example. I'll mention this one. This is interesting. Basically, what these folks at Google did was they hammered this aggressor row many, many times. And then they hammered this other aggressor row very few times. And then they showed that they were able to use bit flips in this victim row, far away from the heavy aggressor. So why is this interesting? It's interesting because RowHammer spans across multiple aggressor rows, but it's more interesting from a defense perspective. So if you hammer this aggressor row, a defense mechanism normally detects that this is the victim row and refreshes this row. Now the defense mechanism can be an attack itself because it's refreshing the aggressor, near aggressor. So you need to be very careful with the defense mechanism because your defense mechanism can become an attack itself. And that's the significance of this paper, in my opinion. And they actually published it at Unix Security in 2022. Okay, so I'm going to talk about solutions. I'm going to switch to solutions a little bit more. So we were actually developing a lot of solutions also. We have some more solutions. We are doing a lot of memory controller as well as NJIT solutions. This is one of the solutions that is interesting to me, although it doesn't work as much as well as it scales to, as RowHammer scales to hundreds of hammer counts, for example. So one of the things that we wanted to do was we wanted to have a scalable solution as RowHammer. For example, if you can induce a bit flip after only 10 hammers, can your solution be good in terms of performance? That's a very tough thing because benign applications, like not attacks, real applications actually access rows hundreds of times within a refresh interval, some of them. Now, the benign application itself becomes an attack, right? So can you actually handle that gracefully with low performance overhead and efficiency overhead? And then the other thing was, can you actually not change DRAM at all? Can you do this purely in the memory control? And this solution actually satisfied both, except not at tens of hammer counts. So let me give you the basic idea very quickly. We have a memory controller-based solution. You have area-efficient Bloom filters and hardware implemented in the memory controller, and those detect which rows are potentially being hammered. And then the memory controller says, oh, this row is being hammered, so it stops accessing that row for some time. And you can actually prove security guarantees by designing this carefully. And then you can optionally inform the system software about the attack. So I think going forward, the solutions need to be compatible with software at the higher level. Once the hardware discovers there's an attack, you can actually push it down into software for more analysis. Okay. So this is a more intelligent controller now you can see, right? It's not just a probabilistic adjacency mechanism. And there are more intelligent controllers that are to be designed, which is interesting. And there are a lot of work in this area. And if people are interested, I would encourage people to do more work in both analysis as well as solutions. They're both important. And these go hand in hand, in my opinion. So what did the industry do? So industry was actually quite silent, or they didn't want to talk about it for a long time, basically. But finally, this is ISSCC in 2023. It's a major circuits conference. SK Hynix published this paper where they basically acknowledge this problem. You can see RowHammer essentially in the abstract. And they basically provide solutions to it. They have multiple solutions. A lot of them are inspired by prior work. some of which we have done. Some of them are probabilistic, and one of them is actually, and they both modify the memory chip essentially. Essentially, they build a memory controller inside the DRAM, as we have envisioned. And I think this is a good direction, except people need to be more open about this, in my opinion. So what they did was, essentially, in one of the solutions, they have counters for each row in DRAM. And this is costly in DRAM. If you think about DRAM manufacturing, people are very worried about cost. If DRAM manufacturers are putting these counters that are not part of the capacity, then they're worried about the problem a lot. And they have a controller that refreshes the just rows. They don't talk about it in much detail. They basically claim in the paper that they reduced the RowHammer vulnerability to 7%, whatever that means. It's very hard to read these ISSCC papers. It's only 2 pages, by the way. But it's, in my opinion, this is a step in the right direction, but it's not, let's say, very open as we would like. So the good news is Samsung also was kind of pushed to publishing their own work on arXiv after they saw that ISSCC had this paper from SK Hynix. It's a very hard to read paper, but you can take a look at it. It's an approximate mechanism for solving RowHammer. But I think the good thing is there's a RowHammer word in the title, right, of a paper written by a major manufacturer. I think we have a lot more ways to go. Okay, the question is, what else is lurking in DRAM and other technologies? Are we now RowHammer free? And the answer is basically no. And there are other redisturbance mechanisms. I'm going to spend some time to talk about RowPress. This is our recent work at ISCA. Essentially, we were always interested in what else is there in DRAM. Is it going to be much worse? In this case, we demonstrate another redisturbance phenomenon, and it's different from RowHammer. I'm going to mention that quickly. And we demonstrate this on real DRAM chips as well as on a real system, not as an attack, but more of a proof of concept. And hopefully you provide effective solutions, but effective is always depend on what you know. What you don't know is what really will kill you, I think, in security in general. That's why I think we need to know more and more by analysis. Okay, so what's the idea over here? Basically, this is the basic idea. If you keep a DRAM row open for a long time, this causes bit flips in adjacent rows. So you activate the row, you don't pre-charge immediately, but you keep it open for some time, and this causes bit flips. So it's not based on many activations, as you can see. It doesn't require many row activations. In fact, in extreme cases, only one activation is enough. And these are not retention errors. This is actually an error that leads to, that's because of disturbance. I'm going to mention that case. So why is this different from RowHammer? Essentially, why is this interesting? Basically, RowHammer mitigations, almost all of them work by detecting high row activation count. Now, what if there was another phenomenon that doesn't require this high activation count? So basically, you built a defense that looked like this, and someone basically bypasses the defense. This is because you built it assuming this is the high row activation count, right? Somebody goes over the low activation count over there. I think we need to be careful about this sort of effect in our systems going into the future. So basically, this is a real example from real chips. Instead of using a high activation count like RowHammer does, what RowHammer does is basically you keep activating the row at maximum frequency. You need 47,000 activations in this particular case. But we show that if you actually keep the row open 7.8 microseconds, which is allowed by the DRAM standard today, you need only 5K activations. And if your RowHammer was configured to protect, let's say, get into effect after, I don't know, 30K activations because you put some guard band, you would still get bit flips, essentially. That's the idea. And in some extreme cases, like if you keep the row open for 30 milliseconds, you need only one activation. This is, I think, fascinating to me. This is still possible to do, but it's not part of the standard. The standard allows you to keep the row open up to 70 microseconds, 70.2 microseconds. 30 milliseconds is still large, but it still gives you an understanding of the device. That's why you need to study these devices better. Okay, so we used our infrastructure to do this. We actually did a lot of studies on these chips. And I think I already mentioned this, but let me give you some data. Essentially, you amplify redisturbance in DRAM. If you keep the row open for a longer time, you reduce the minimum number of row activations to cause a bit flip by 1 to 2 orders of magnitude. So this is RowHammer from one manufacturer, I think Samsung. Yes. You need bit flip. You need this many hammers to cause bit flips activations, and this keeps reducing. At 70.2 microseconds, you're 2 orders of magnitude lower. And at 30 milliseconds, which is not allowed by the standard, you have 1 activation to induce a bit flip. Fascinating. And this is different from RowHammer based on our understanding because this is a very nice relationship with temperature. As temperature increases, these bit flips get worse. We cannot say the same thing about RowHammer at all. And also a different set of cells are affected compared to RowHammer. and access pattern differences, temperature change, etc., are all different. Essentially, everything we know about RowHammer, this behaves different. Okay, so we also showed this on a real proof of concept system using an Intel Core processor and Samsung module. Samsung module has protection for RowHammer. Essentially, we wrote this program, which is not easy to write, but you can download it. All of this is available online, which accesses different cache blocks in an open row to keep the row open, or to force the memory controller to keep the row open. And we essentially find bit flips in real systems. And if you access, for example, 32 blocks, 32 cache blocks in a row, you get bit flips. You start getting bit flips. And there's more analysis in the paper. And if you're interested, you can download this code. We'd be happy to help. We have helped people to actually replicate this also from industry. So if people are interested in doing this, we're of course very interested. Okay, so how do you mitigate this problem? There are many mitigations possible. One of the mitigations is changing the DRAM chips. I think it's actually interesting to look at. But we actually piggyback on RowHammer solutions. Our key idea is to essentially limit the maximum row open time for some amount. Hopefully you limit it not so unreasonably so that you don't lose row buffer locality. And then once you limit the row activation time, adjust your RowHammer mitigation such that the tracking, the aggressor row tracking takes into account the reduction that happens because of RowPress. That's the idea. And at different levels of row open time, you have different levels of reduction clearly. And if you limit it, it makes your life easier so that you don't need to look at this part of the curve over here. And we show that this actually leads to secure mitigation. Unfortunately, there's a little bit more overhead. We show that it's not too much overhead, but unfortunately, there are some applications that always see some overhead. So in the end, I think security has a price. Okay, so again, this is all artifact evaluated. It actually got the best artifact award at ISCA. So my student Halson worked a lot to make it really nice and reproducible. So if people are interested, we're happy to support it. I believe there's more to come. I don't think this is the end of bit flips. That's why I think the answer to my question, the title is, are we free of bit flips? Can we be free of bit flips soon? I don't think so. It's just a matter of creativity and discovery. We need to discover these bit flips so that we don't encounter them in the field, in my opinion. It's better if we encounter them in papers so that later works actually solve them so that they're never encountered in the field. Right? Okay, that's why I think we need to understand a lot more and we need to develop solutions. Basically, understanding, I think, requires a lot of things. And there's a huge space that we don't quite understand, in my opinion, even though there's a lot we have understood so far: aging, other environmental conditions, memory access patterns, memory control and system design decisions. These are actually things that affect bit flips. And maybe there are other new bit flips. If you actually understand these more, you can find other things that may happen under different conditions that may be different from RowHammer and RowPress. And I think solutions are actually going to be important because we need more in-field patchable, reconfigurable, and programmable solutions so that if we encounter them in the field, maybe we do some of this testing in the field also, because we may not be able to test all of our chips before we put them out in the field, but in the field, we can do some testing, and over time, the chips become better so that because we know about them more. And I think that I'm actually a strong proponent of this. Going forward, we need to have a lot more online testing, online intelligence architectures that can become better over time based on what they see in the field. Just like kind of humans do, right? We hopefully, not always, but we hopefully become better based on interaction with the environment. Our machines should be able to do that also. Okay. So that's one thing we argue in our recent survey. How much time do we have? 4 minutes. Okay. So okay, I can take questions a little bit right now, and then we can continue. Yes.
Yeah, I have a question. Is there any way you can repair the vulnerable rows? So for example, you see that bit flip in a system.
Yes.
Any way to repair that?
Yeah. So if you, for example, if you find the bit flip online during online operation, you could, there's a mechanism called page offlining. You could offline that row, offline that page. And this is used when people find memory errors in the field, for example. It's used in data centers like Facebook, Amazon, etc. That's one mechanism. It's a heavyweight mechanism, but you could use it today. There are also lower level mechanisms that people have proposed that are not used today, like bit level repair mechanisms that require some programmability in the DRAM chip or the memory controller. But it's a similar idea, basically. You either offline the row, take it offline so that nobody uses it, or you remap the vulnerable bits to somewhere else. Yeah. That's a very good question. I think we need to look at those mechanisms going into the future more and more as things become more vulnerable.
I also have one question, Onur.
Yes.
Understandable why like big companies, especially these like 3 DRAM manufacturers, they want to kind of guard their process technology.
Mhm.
Because of course, this is like something that they can make significant competitive like advantages from them. But it's not obvious like why they are protecting their like RowHammer mitigation mechanisms. Because like if they do that, they would it will open a door like for the like the other like the startup companies or the industries or the academia to help them kind of, right?
Yeah. Yeah, I agree. I think certainly if they are more open, they could get more help from others. And that's what we argue in this paper, actually. I like that thinking. Basically, we argue a little more transparency, maybe not full transparency. I think the reasoning is, so there are multiple answers that I have in this. Basically, I think it's a very entrenched industry over time. Like DRAM has been around since 1965, and this industry has been around for 40 years or so. And they have their ways. It's a very commodity-driven industry, right? So margins are low and there's a lot of competition. So the mindset has been always, we do closed operation such that we protect for a very little margin to begin with, right? So I think that mindset is affecting that. Partially it's the mindset. They basically worried that if we actually, for example, give out the RowHammer mitigation, it would give information about the underlying device operation or underlying manufacturing process. But I think we need to change that mindset. I think more than anything else, like if you can enable more clock-taking process system stack, this could actually add a lot more value to the memory manufacturers also. I think it's the business model is very commodity, but going forward, maybe a better memory business is not just a memory business, but memory plus computing business. Like this also works nicely with compute and memory solutions. And these manufacturers may be packaging solutions as opposed to just memory. So if that mindset shift happens, I think people will be much more open. I hope that happens. That's what we're trying to do. Okay, maybe I'll conclude very quickly with some slides. So basically, I think that kind of nicely segues into what I'm going to mention. I think we need better communication between DRAM and controllers. I will mention one thing. This is some work that we've been doing. Basically, we want to partition the duties between DRAM and controllers a little bit better. We call this self-managing DRAM. Essentially, the idea is, so one of the reasons why DRAM manufacturers cannot implement sophisticated solutions, they're basically bound by the interface. They have very little time to operate, and the interface is very rigid. If you have a better interface between controller and DRAM, for example, DRAM can say, oh, I'm dealing with RowHammer problems internally, don't bother me, it would give them a lot more freedom to fix these things. And that's what we argue in this work, basically. If the DRAM is able to reject some of the memory controller commands, they could actually do a lot better management. So this is very low overhead. I'm not going to go through the details, but you can actually implement different refresh mechanisms, different RowHammer protection mechanisms, different memory scrubbing mechanisms, essentially things that DRAM manufacturers can actually understand very well internally inside the DRAM system. And I think we need to look at better interface between memory and controllers going into the future. Okay, this was part of my PhD student Hassan's work, so you can take a look at his presentation. There's more RowHammer solutions I will mention. I'm not going to talk about it. So future challenges. I think future is much worse. Basically, it's actually, in my opinion, due to these issues, I believe that there are some areas that may already be slipping into the field, but we may not be able to seeing them easily, right? People have found out this one, for example, silent data correction in processor chips, right? Google and Facebook made a big deal of that. I believe there's a lot more in the memory space that's happening, but that are not getting publicized, let's say. So refresh, for example, are retention errors becoming worse, and are they exploitable in the field for security? I think that's very interesting. And I think no technology is immune, unfortunately. Emerging technologies are fascinating, and it's great that people are examining them, and I think they should be examined. But I believe that all of the technologies will have similar issues. And in fact, there are papers that talk about RowHammer in some STT-MRAM, for example, and maybe other things. But there's more to do in that. Okay, I'm going to skip this one, but basically, I think I already mentioned that we need to understand more, we need to architect better, we need to do better design and tests, especially online. That's why we've been building this infrastructure, and we'd be happy to help anyone. Now, let me get back to these bridges. I like these bridges. So this is a bit flip, critical infrastructure. Human beings have been designing bridges for thousands of years, right? And we still didn't get it right. You can see that these bit flips happen once in a while. You probably can recognize some of these places. This is in Pittsburgh, where I used to live. It's a bridge that I used to go over many times, and it collapsed, and we still didn't get it right. So can we actually get it right in bridges? I don't believe so. We will have these bit flips, and I think the good thing is we're much more fortunate in computing, meaning computing doesn't require heavy infrastructure like this. This didn't move for some reason. But yeah, basically in computing, it's much softer. We can avoid a lot of these failures by routing around things, right? If you have a patchable memory controller, for example, you could fix these issues, in my opinion. Okay. So let me give you some final thoughts very quickly. I will mention some prior work that I think is fascinating. This is a work that was published in IEEE Security and Privacy in 2002. How many people know about this work? People may. Anyway, it's not as famous as RowHammer, but it has the same kind of thinking. The thinking is you could induce memory errors and you could take over a virtual machine. Unfortunately, the way they induced memory errors was what was possible at that time. They could have lagged next to the memory chip over here, so they got a lot of memory errors. But once you get those memory errors, you can have a probabilistic attack that could take over the virtual machine. Essentially, what RowHammer did was RowHammer replaced that lamp with software. Now you have a much more precise way of inducing bit flips, and anybody can induce them. You don't need to have physical access to somebody else's computer, right? As people have shown. So I think that's what's fascinating about RowHammer. And as a result, I think security folks got quite excited about RowHammer also because they could do this in software. Whereas even though this was published at top security venue, not many security folks went ahead and started putting lamps next to next to people's computers, right? So it's interesting though. It's interesting to look at. Okay. I'm going to skip some of this, but maybe I will mention one thing. So I think more than the papers, etc., I think the mindset effect of RowHammer has been very interesting because hardware security folks became a lot more interested in hardware, or security folks in general became a lot more interested in hardware. So if you look at security venues, like before RowHammer time, let's say, there are hardware security papers, etc. There are some side channel papers, etc. But it's not mainstream. Right now, if you look at a security venue, sometimes there are RowHammer sessions. Right? There's a lot more hardware security sessions. So people are actually a lot more interested in the inner workings of hardware, and they actually want to figure out what's going on so that they could exploit them and they could build defenses against them. I think this is great because they're really the frontier of security is moving from software high-level bugs to lower-level hardware. That's why I think the title of that article, now hackers are exploiting physics, is quite fitting. And it's also interesting. So basically, there's more to come in terms of attack. I should say that the attacks are becoming more difficult because people are raising the bar in terms of defenses. So it's not going to be easy to break future memory chips, but I believe it's going to be possible unless we actually have future-proof solutions. And solutions also need to be coming. I've also mentioned that, I think I already mentioned a lot of this, people who looked at Meltdown and Spectre, people who discovered that, two of the three groups that have discovered them worked heavily on RowHammer before. So these folks actually really delved into hardware with these bit flips. I think there's more to do over here. So there's a lot more to come in hardware security. So let me conclude. I think memory reliability is reducing. Hopefully I've convinced you of that. Reliability issues open up new security vulnerabilities as well. These are very hard to defend against. RowHammer is a prime example of this. As I mentioned, it's the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. I think the implications on system security, safety, and robustness are tremendous and exciting. And again, I think this spans all the way from devices to algorithms and software.